Okay. Better? Worse? Better. Okay. Am I mic'd? Can you hear me? I can never tell. Yeah, excellent. How are we? How was that last class? It was, okay. Awful. Awful? Someone said awful? All right. It was groundbreaking. It was mind expanding. It was the first taste of the evil side of statistics, but hopefully it gets better from there. So a reminder, I'm off to San Francisco today. I will not be here on Friday, but we will still have a class. So the link to the YouTube broadcast is on the website. If for some reason you can't find it, if you go to my personal website, which is mylastname.com, click on video, it'll be there as well. So you don't have to come to class on Friday. However, this classroom will be available to you if you want to come with your computers and use the Wi-Fi. So the way it'll work is I will share my screen with the video feed and I'll talk like this. You'll hear me quite clearly. If you have a question, tweet me. All right. My Twitter name is Dionandan. So if you haven't got Twitter, get Twitter. Right. And it will be open to the public as well, but they won't be tweeting, won't be responding to their questions. Well, I can't tell who's tweeting, to be honest. But no one ever has any questions anyway. So I don't anticipate a whole lot of questions. We've done this before in other classes and it's worked out pretty well. And if it doesn't, we'll go over the material anyway on the next class. So exciting, huh? You have to come to class if you don't want to. But you're still responsible for the lecture. And of course, the recording will be made available on the website as well. So if you don't want to watch it live, it'll also be there. Any questions about Friday? Whole new world. Okay, so we're continuing on with inference. We started inference last time. And inference, as we remember, is all about doing stuff to a sample to learn about a larger reference population. So we have a reference population, we have a sample, we do stuff to it, we make some conclusions, and we infer things about that sample. So last time we talked about the normal distribution at length, at nausea. Why do we talk about normal distribution? I had like 4 lectures on it. I've bored you to death about the normal distribution. Have any idea why it's important? After all that, you have no idea why it's important? At least 4 of the greatest mathematicians of all time have built their careers on the normal distribution. It's the foundation for the science of statistics. You don't know why it's important? It's important because it probably describes the frequency distribution of most natural characteristics, certainly most human characteristics, and it's the foundation for the tests that we end up doing to compare whether or not our sample is less or more probable to belonging to the universe of samples. All right, that makes a little sense. We talked about the Z distribution. Yes. Mic is not on. Oh, you're right. See, someone said I was Mike and you lied. It was you. You lied. Blame that guy. All right. So now the lack of answers to my questions is explained by the lack of miking. From this point on, I expect full answers to all questions. We talked about the Z distribution. What is the Z distribution? What's the Z score? Yes. Exactly. The number of standard deviations away from the mean is a Z. It's a Z measurement. A Z distribution is a special case of the normal distribution in which the mean is 0. So it's the perfect normal distribution. There's so many distributions out there, like literally scores, if not hundreds. And we're going to learn a bit about the T distribution today, which is another special case of the normal distribution. That's really the focus of Friday's talk, the T stuff. We're going to hear about something called the binomial distribution, which you're not responsible for, but I'd like you to know what it is. And statisticians love their distributions. And it's a difficult thing to wrap your brain around. So if it's not something that's intuitive to you, don't worry about it. Just accept that they exist. Okay, so inference. Again, the process of drawing conclusions from things that are subject to random variation. So if I take the average age of my class here, that's supposedly subject to random variation. It's a random selection of your ages. Not entirely true, because depending upon what year you are in your program, you're likely to be probably the same age, because our system is built that way. But plus or minus weeks, months, whatever, there's some random variation in your ages. So we talked about the null hypothesis and the alternative hypothesis last time. This was an example of hypothesis testing. Remember, the null is denoted by that symbol, H sub naught, and the alternative is H sub A or H sub 1. And what's the null hypothesis? What's essentially saying? Love it. Nothing's going on, okay? Or equivalence. That's another way of looking at it. So very often we're comparing two groups. If they're equal, there is no difference, there's nothing going on. And the alternative is something going on, right? So we talked about type 1 and type 2 errors, and I use the court case as an analogy for this. So a type 1 error is when an innocent person is convicted, and we never want that. So we want very low type 1 errors. Or in other words, we're thinking that a drug doesn't actually work, but we think it does. Okay, so we don't want things that don't work in our marketplace, and we don't want innocent people being convicted. A type 2 error is when a guilty person is let free. Also a bad thing, but we're more accepting of that than we are of an innocent person going to jail. And the equivalent of that in medical science is that something that actually works is not considered to work because it didn't meet the threshold of proof that we typically accept as being quote unquote working. Type 1 and type 2 errors. Type 1 error we denote by alpha, and type 2 error by beta. So directionality we talked about as well. So if you want to know if something is bigger or smaller, we use a one-tail test. If we don't care if it's bigger or smaller, we just care that it's different, we use a two-tail test. And it's called a one-tail test versus a two-tail test because a one-tail test only looks at one end of our normal distribution, and the two-tail test looks at both ends of the normal distribution. In other words, is the mean of my class, is it in this extreme zone here of my normal distribution, is extremely less than everyone else's, or is it either extremely less or extremely high? In either one of those cases, I say it's very different from the expected norm. Therefore, it's statistically significant. That's what statistically significant really means. It's extremely different from the expected norm. Okay. Now, the new stuff. Before we go on new stuff, you want to stop me and talk about the old stuff again? Okay. Excellent. New stuff. We have these things called probability density functions. Don't worry about probability density function too much. It's just that. It just means that underneath this curve, we should get 100%. And once you compute the density, that gives you probability. So a normal distribution can be considered to be a probability density function. It's a frequency distribution, but it's also a probability. So if you distribute IQ scores from, let's say, 10,000 people, 10,000 kids, 10-year-old kids, we have a mean of, let's say, 100 and a standard deviation of 15. So looks like that, right? So here we have the mean here, and we know that these are standard deviations. So one standard deviation across gives us about 65% of the cases. 2 standard deviations gives us about 95% of the cases. 3 standard deviations gives us about 97% of the cases, and so forth. Remember the 3 sigma rule, right? So if somebody has an IQ of 130, then there are exactly 2 standard deviations above the mean. So under the z-score dynamic, we'd say they have a z-score of 2 above the mean, right? Because the mean is 100 should be 130 is 1, 2. That's right, 2 standard deviations, because standard deviations are 15. 1, 15, and 30. There it is. Okay. So z-score of 2 corresponds to an area of about 2.3%. So there. So 2.3% of cases are greater than 130. Here's 130, right? So we know that we have a probability of 2.3% of randomly selecting a child in our superpopulation with an IQ of 130 or greater. So visually, hopefully that's obvious. That's how this all works. Right? So we know the mean is 100. We know the standard deviation is 15. How do we know that? Because we know that. We've done a lot of experiments on this. We know it. Okay. If we take a random selection of 25 kids from some downtown school, measure their IQs, would we get a mean score of exactly 100? We know that the larger mean for everyone in the world is 100 for 10-year-old kids. If I got 25 kids, I took their mean, would I get exactly 100? Obviously not. Why wouldn't I get 100? The one guy who answered all the questions is away today, so someone else has to step up. Why wouldn't I get exactly 100? If I know the mean age of second-year students is 22, I took the mean of this class, would I get exactly 22? No. Why not? Yes. Well, that's part of it, but that's the real reason. Why are you exactly 22? No, you're not. Is he exactly 22? No, he isn't. Why not? Because you're different people. Because there's some differences. There's random variation. Any two groups are going to be slightly different. The super mean IQ may be 100, but the means of small groups chosen are going to be a little bit different from 100. Okay, why not? Because I'm going to get all kinds of things. Variability. There's also something called sampling error, which means that maybe I've chosen the wrong chunk of people, or I have some bias built into how I've chosen my sample. I haven't got 25 random kids. I got 25 kids who are held back, you know, or 25 of the slower kids have lower IQs, right? All these things are possible. So if I chose 25 random kids, I might get a mean IQ of like 98.2, 101, 105, whatever it might be. So rarely is my sample mean exactly equivalent to the general population mean. So rarely is my statistic equal to my parameter. If it was, we wouldn't need the science of statistics. Every sample I took would be precisely representative of the real world, right? So where does that take us? So I was wondering, how representative is my sample then? So let's say instead of taking one sample of 25 kids, I took 100 samples of 25 kids. Okay, so got one sample here, I take their mean, and I get something like, 95. Another sample, I take their mean, I get something like 98. This sample there, I take their mean, I get 102, and so forth. Every sample is going to give me a different mean IQ. That's obvious, I hope. By the same token, if I took a bunch of second-year classes and I took the average ages, I'm not going to get 22 every time. I'm going to get like 21 and a half, 22.3, whatever it might be. However, is it unreasonable to expect that if I get 100 samples of these kids, that their mean IQs will be somewhere around 100? Is that unreasonable? It's not unreasonable, especially if I tell you that the overall average for all kids in the world is 100 IQ. So I expect that my sample mean will gravitate somewhere around 100, not precisely, but around. So having said that, if I were to collect an infinite number of samples, blew your mind, right? Okay, not 100, not 1,000, an infinite number of random samples of 25 kids and took their mean IQs, what do you think the mean of those mean IQs would be? Be 100. Isn't that magical? That's the revelation that allows all this to happen. And that's really the central limit theorem. This idea that the mean of the samples of an infinite number of samples equals my parameter. Every year I plan to do this, and I always forget to do it. Bring in a jar of jelly beans in this lecture, and I forget. And I would ask you to actually guess how many jelly beans are in the jar. It's a difficult thing to do because once you hear the first guess, there's a bias that kicks in where someone else tries to guess near to that person. So the first person sets the tone. But if there's a way to set it up so you cannot see what she picks, right, like a Google spreadsheet or something, at the end of the class, we'd compute the average. And an amazing thing tends to happen. If you get enough estimates, the average of your estimates tends to be pretty much the same as the true number in the jar, unless people are completely, oblivious to how to count jelly beans. Right? Right? And that's something like this. It's the idea of You get enough samples, the mean tends to gravitate towards the truth, or the parameter in this case, right? So we have this population mean. Here's the truth. Here's 100 IQ points. And each of these samples is chosen, blah, 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 blah. So a graph of all of our infinite samples, of all the means of our infinite samples, would be distributed exactly like a normal distribution. Because some of our samples would have low means. Some of our samples would have like genius kids over here, but most of them would be right here in the middle at exactly 100. And so the mean of this theoretical super distribution is our parameter mu. It's magical. Magically that happens. So we call that the sampling distribution of the mean. Okay, I'll say it again. The sampling distribution of the mean is this theoretical distribution of the means of a theoretical sample done a billion, trillion, billion infinite times. Mind you, each sample has to have the same size. So I can't choose like 10 kids here and 25 kids or 100 kids there and create a distribution. It makes no sense. So I got to choose a consistent number of kids. Okay, this is theoretical again. We cannot, obviously, we cannot choose an infinite number of samples. We can choose a lot of samples. We can do this a billion times. It's been done, you know, just to show that it's asymptotic. It approaches our mu. But again, the sample distribution of the mean is a theoretical distribution. So we mentioned the central limit theorem a couple times. The central limit theorem essentially says that the mean of this theoretical distribution is our parameter. It's magic. It's magic, right? So amazing thing happens here too. So let's say that the means within the samples are not normally distributed. It doesn't matter. The means of this theoretical distribution is normal. So even things that aren't really normally distributed tend to be normally distributed if we take their means only. And that's a wonderful saving grace. It allows us to apply a lot of our statistics that derive from the normal distribution, even to things that are not overtly normally distributed. So I'll say it again, a characteristic that is not overtly normally distributed in our population, like, I don't know, I'm trying to think of something. Blood pressure is not normally distributed, but mean blood pressure from a variety of samples, if you take their means and plot them, then those means are normally distributed. That allows us to do statistical tests. Okay, next we have something called the standard error of the mean. What the hell is that? The standard error of the mean is the standard deviation of that theoretical thing that we just talked about. Right, so we have our infinite number of samples. So we've got 25 kids chosen infinite number of times. I've got their means plotted like this. Standard deviation, we're going to call this the standard error of the mean. It's an important technical term, SEM. Right? So the larger my SEM, the less likely that this superpopulation is in fact representative of reality. The wider it is, the larger the standard deviation, right? But the tighter it is, the more likely. Let me go back here for a second. Let me make sure I got something on here. This slide is off the screen. We're okay. We're okay. Okay. So like the last time, we want a tighter distribution. We don't want a wide SEM. We want a small standard deviation. But they're never known. The actual standard error of the mean will never actually be known. Why will it never be known? Why can I never know the standard error of the mean? It's the standard deviation of a theoretical distribution. So why can I never calculate the standard deviation of a theoretical distribution? Yes?
We'll never have the infinite number.
Because it's a theoretical distribution. What's the hair color of God? Oh, because it's a theoretical construct. Yeah. Okay. We can estimate these things, right? We can estimate it by using the things that we do know. We do know the mean of our sample. If I grab 25 kids and the cops don't catch me, right? I can calculate the mean IQ in that sample. I can calculate my standard deviation because we did that a couple weeks ago. I know the n is 25. So I just use this formula. The standard error of the mean is just the standard deviation of my sample divided by the square root of the number of people in my sample. That's just the formula for it. It's not exactly the same as standard deviation. Why? Because if it was the same as my standard deviation, then I got like an infinite number of samples. Each of them has different standard deviations, right? It can't, which one is going to represent the thing that I'm computing, my SEM? Well, all of them can't. So it needs a modifier to show that, in fact, the true SEM is actually less wide than my standard deviation. So I divide it by something to make it less wide. And that thing I divide by is the square root of my n. Okay, back up for a second. We can never know the real SEM because it's theoretical. It's the face of God, whatever it might be. Okay, it's a theoretical distribution of an infinite number of samples. What we are saying is that we are estimating the SEM based on the standard deviation of the thing that we do know. We know things about our sample. So I have you as my sample of second-year students. I can do things to you mathematically, right, to teach me about the university population. I cannot know the standard error of the mean age of second-year students. I can know the standard deviation of your mean age, and I use that information to estimate the standard error of the mean of all second-year students. The larger the sample size, the smaller the SEM. That's what that formula tells us, because it's standard deviation divided by the square root of n. The larger n, the smaller the SEM goes. And that's an important insight. It means that the more sample I have, the less width I have in that distribution, the less error I have, less variation, the more likely it is that my mean is encapsulated in that tightness. So I want a low SEM, right there, it's in the name, error. We want less error, right? And low error means high n. Okay, so back to the IQ. This is how IQ is distributed, and we see that in the country as a whole, but it's really superpopulation. The mean is 100, 2 standard deviations takes us to 130, and so forth. We have a sample of 25 kids, and let's say in my 25 kids, I've given them all IQ tests, and their average IQ is 101. Okay, the standard deviation of the sample is 10.5. What can I do with this? What I want to do with this is to estimate the average IQ of 10-year-old kids. I can't just say it's 101 because that's just the IQ of my 25 kids. So here's my summary of my information. The mean is 101, standard deviation is 10.5, and the number of kids is 25. First thing I do is I estimate my standard error of the mean. We said that's the SD divided by the square root of the n. That gives me 2.1. If the sample was really large, let's say it was like 225 kids, my SEM would be even smaller. It would be down to 0.7 if we do that calculation, right? That shows us right away that more n, higher the SEM goes. Okay, so let's do that first example then, 2.1. So we have a mean of 101, an SEM of 2.1. What does that let us do? It means we can compute the population parameter, or estimate the population parameter. Why do we compute the mean to begin with? Because that's our goal here, to estimate the parameter. We compute a statistic to estimate the parameter, right? So this allows us to estimate the population parameter within a certain degree of confidence. And that confidence is defined a little bit by z-scores. See what that means? We want to know within a certain amount of confidence whether our sample mean is representative of the true population mean. Because even though I've told you the population mean is 100, you don't really know that. We know that because we've done this a billion times. We don't know that yet. What you have is a sample of 101. You want to know, is 101 representative of the entire population of 10-year-old kids, right? Last time we talked about confidence levels, alpha levels, type 1 error levels. I'm going to say, I want to know this within a 95% confidence. 95% means my alpha is 0.05 because it's 5% less than 100. That's a type 1 error. Okay, so let's do this. What z-score corresponds to a 95% chance of getting a population score close to M? So how you get that? You go to a z-score calculator and you look up what 95% is. It's 1.96. Okay, back of your book, z-score calculator. So 2 standard deviations, 2 z-scores is about 95% of my curve, right? We're all clear on that. That's kind of cool. That's kind of important, right? 2 what? 2 standard deviations. That's what that means. What is the standard deviation in this situation? What number is the standard deviation in this situation? And this is the insight that's kind of critical to doing these kinds of problems. So we've already computed our standard deviation earlier in my sample, but what I care about is whether or not my mean is within 2 standard deviations of a population mean of a parameter. In this case, I'm not using the standard deviation of my sample. I'm using what? The standard deviation of what? Echoing silence. Most silent class overhead ever. I attribute that to my remarkable good looks. I've stymied you into stultified silence as you gaze upon perfection that is me. So look away, cast your eyes away and think about the question again. I'm estimating the parameter of this theoretical superpopulation. So I need a standard deviation to do that. Is the standard deviation from my sample or is it from the theoretical superpopulation? Take a guess. It's 1 or 2. There you go. I know you think you're being stupid by saying the obvious answer. Just play along, okay? And the standard deviation of a theoretical superpopulation is that. Because we said the SEM is the standard deviation of the sampling distribution of the mean. So that's what I care about. So in other words, I want to know, is 101 within 2 SEMs of this thing that I don't know about yet, my parameter? And that tells me that has a 95% chance of being in that range. Okay. Now, if I'd use a larger n, then, oh, you can't really see that, can you? This conversion to Google Slides has really made things large. Let me see if I can bump up the, there we go, that's better. Okay, so in other words, you have a 95% chance that all of the sample IQ means are no more than 2 standard deviations above or below our mean. So our SEM is 2.1. What's 2 times that? 4.2. Where'd my thing go? Oh. Okay. Okay. So 4.2 above 101 is 105.2. 4.2 below 101 is 96.8. In other words, I can be 95% confident that the true parameter, the true standard mean, the true mean of IQ in my superpopulation is between those 2 values, and that's in between them. See what I did there? All right. I constructed a distribution of probable IQ scores of my superpopulation. I don't know what the mean is. I know what the mean of my sample is. That's 101. So that goes in the middle. I don't know how wide to make it. the width is going to be my SEM. That's what I did. SEM times how many standard deviations? I chose 2. Why? Because 2 gives me 95% of all outcomes. So 2 standard deviations above, 2 standard deviations below gives me a range of 96.8 over here and 105.2 over there. So that's my confidence interval, my 95% confidence that in between those two numbers is the true mean IQ of 10-year-olds. Whew, that's a lot of stuff. If I had a larger sample, instead of 25 kids, I had 225 kids. My SEM would be 0.7. Doing the same stuff, I would get this range. I would get a range of 99.6 and 102.4. Which range is tighter? This one or that one? The second one or the first one? Which is a tighter range? Second, thank you. Second range is tighter. So that tells us right away, a larger sample size gives me greater precision in my estimation. Gives me a tighter range, confidence interval. Okay. We could do the same thing using 99% instead of 95%. What alpha level would 99% correspond to? If I want to be 99% confident that my estimate falls in this range, what's the alpha level? Yes.
0.01.
That's right, 0.01. So 1% is my alpha. Okay. So if I want to set my confidence at 99%, which means that, what this means is that my mean, I'm 99% sure falls in this range here. Anything beyond 99% is over here. But 99% of my infinite number of samples will have means in here. Okay. How would I go about doing one for 99% instead of 95%? For 95%, the first thing I did, I looked up the Z-score that corresponded to 95%. That was 1.96. So what am I going to do here? I'm going to look up the Z-score that corresponds to 99%. That's 2.33. So how's that look? Well, we can just use 2.33 times my SEM. And that gives me my range. I don't know if I did it here. So there are two basic approaches we talked about last time. Parameter estimation, that's when we estimate a parameter and an error range. We just did that. We estimated what the mean of IQ is, and we computed an error range. And the other way is hypothesis testing. We did that last time when I said, is my mean IQ equal to 120? Let's do a test and find that out. Both are valid ways of answering the same question, but different mathematical approaches. We did hypothesis testing last week. We tend to like the first type better now in science. Parameter estimation is more in fashion because it gives us a range to play with. It's more diagnostically useful. Even though all the textbooks and all the stats classes will still have you doing hypothesis testing. And of course, on your exam, there's a lot of hypothesis testing where you're stating null hypotheses and alternative hypotheses and rejecting the null, or what's the opposite of rejecting the null? Failing to reject the null. Thank you very much. Okay. But in practice, in real science, we tend to prefer parameter estimation, doing the stuff we're doing today. So we estimate a population value, i.e. the mean IQ of all 10-year-olds or the mean age of all second-year students, and we compute a range, some kind of interval that goes with it. So again, the mean age of university students is 21 years. This is the way I report my confidence. Okay, the actual parameter estimate, well, you can't see the arrow there, is 21 years. So that would be based on some experiment I did, some analysis that I did, some sample that I collected. I got you guys in the room, let's say your mean age is 21. Once I use your standard deviations and your ends, I use my Z numbers, I have this, I have my confidence interval. You've probably seen this in some papers already. If you haven't, it's your first time, that's great. The way we write it, we have a point estimate and two round brackets and a comma. And what these brackets mean is the real parameter estimate is somewhere between these two numbers. Okay, and usually it's given with a confidence level. If it's not given, we tend to assume 95% is the confidence level. If 95% is the confidence level, then my alpha, or type 1 error, is 0.05. What this means is, in this big distribution of probable values of my mean age of university students, 95% of the time it's going to be between 18 and 21.5. Right? And obviously, is it possible to have this number be outside this range? Is it possible? Yes or no? Yes? Who said yes? Why is it possible? Yeah? Okay. No. Thank you for answering those. Very brave of you. So it's a common misinterpretation. This is our estimate of the parameter. And we're saying we think it's this, and we think this is the amount of error in that estimate. The true value might be outside that range, but this is not what we're saying here. We're saying we're sure, according to our analyses, this is what we think it is. So this is always in between our errors. Technically, we think it's a little more likely to be that than to be in any one of these extremes, but don't think of it that way. This is the range of probable values 95% of the time, and this has to be inside there. This is what we're reporting. I think it's 21. Are you sure, Ray? Well, I'm not entirely sure. It could be anywhere between 18 to 21.5, but I think it's 21. I'm never going to say, I think it's 24. Are you sure, Ray? Well, I'm not entirely sure. It could be anywhere between 18 and 21.5. But you said 24. Yeah, that makes no sense, right? So our range has to include our point estimate. Again, this is not truth. This is our best approximation of truth. She is right in saying that there's a 5% chance that it's not in that range. But what we report as our point estimate must be in that range. Okay. A point estimate involves a calculation of a single value, that 21 there. It's just a description, like a mean, a statistic. The interval is the range in which our parameter has a possibility of lying within a certain confidence level. And that's why that word confidence keeps coming up. That's why I spent so much time doing that 5%, 95% alpha level stuff, because where we set our confidence is how tight or wide our range is going to be. Okay, so let's compute some confidence intervals. Confidence interval designates the range of values within the parameter has a 95% chance of lying. It could be a 99%, could be 94%, could be 12%. I have just said 95% because for some historical reason, we have chosen that as being what we tend to use because we like things in fives, right? Very often it's 99% because 99 has a much psychologically pleasing tone to it. I'm 99% certain that my value is this, that the mean IQ of kids is 101. I'm 99% certain, right? I could be 99.5. I could easily report those things, but we tend not to. And I will probably not ask you to either. So your alpha is either going to be 0.05 or 0.01. And if alpha is set at 0.05, then it's a 95% confidence level. If it's set at 0.01, it's a 99% confidence level. Because again, the alpha is the amount that I'm not confident. The amount of type 1 error there might be, in other words. Okay, so the confidence interval is the confidence limits, the upper and lower limit of what is probably the parameter estimate based upon my sample estimate. So how do we do this? We need the sample mean. We need the estimated SEM. How do I compute SEM? Again, you saw it like 10 minutes ago. Remembers? Yes? Exactly. Standard deviation divided by the square root of n. Okay, so again, we're using what I know from my sample to estimate a characteristic of this theoretical distribution of means. So we need a mean, we need that, and we need well, it says here the value corresponding to the area from the theoretical, blah, 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 blah. That's a complicated thing. What we're saying here, we need to know how much of this curve we want to be confident about. I can be really, lame and say, I only care about whether it's, 1% confident. I mean, that's not really useful, right? Notice I didn't say Z value here because we're not going to use the Z distribution. We're going to evolve a bit. We're going to use something called the T distribution. Why? Don't worry about why. Accept that for confidence intervals of means, we use values from the T distribution. Now, what is the T distribution? It's almost the same as the Z distribution, almost the same as the normal distribution. It's a kind of normal distribution. It's bell-shaped, it looks like this, and its only difference is that it's a little fatter and shorter, and the more N there is, the more people we have in our sample, the tighter it gets, right? So the more N there is, the more it resembles my Z distribution. Remember, the Z distribution is the perfect normal. So all the examples we've done so far use a perfect normal distribution, as if the world is perfect. The world is not perfect. The world varies a lot. So a T distribution allows for the differences in quality that sample size gives us. I'll show what this looks like. So here we go. So the taller ones have more people in them, taller and tighter. That's a T distribution. Now, it uses something called the degrees of freedom. You're going to hear this a lot, degrees of freedom. You probably heard it in high school math class. You hear it in physics class, and no one ever defines it for you. I'm not going to define it for you either, except to say degrees of freedom is just the total sample size minus 1. Okay, let's talk a bit about why that is. I mentioned that with the T distribution, the more sample we have, the more like the Z distribution it becomes, the more perfect it becomes. So we want more sample. So that's why this shows us that as sample goes up, it gets better. But instead of saying N's, I'm saying DF's, degrees of freedom, because technically it's not an N, it's an N minus 1. Why minus 1? Because what it really represents is the number, okay, I'll say this and really piss you off. It's the number of vectors in an infinite random, number of dimensions in a random vector. It means nothing to you, right? But what we think about is the number of things that are at play, free things that are at play to define the scenario. What are at play here? Well, each person in my sample is free to be at play. You're free to be X numbers of years old. You're free to be X numbers of years old, etc. I have no control over that. So the things I have no control over is what I'm measuring. Why is it minus 1? Because technically, I also have the mean age. So if I have the mean age, I don't need all of you to give me information. I can compute the last guy from the mean. Right? See how that works? So that's the mathematical explanation. Don't worry about that. You don't need to know that. If you're intellectually curious, that's why I gave you the reason for it. But the bottom line is T distribution gets more perfect with more N. We define more N's as being degrees of freedom, and degrees of freedom are N minus 1. That's the formula for it. So it's called actually the student's T distribution. And it's the precursor to the t-test, which we'll do on Friday via YouTube. Do you know why it's called the student distribution? Nothing to do with students. Maybe another story? It's the guy's name. It's not really his name. It's his fake name. Why do you call himself student? Stupid name. All right. So very often this is taught in math classes. This is for students. Students must use the t-test. No, it's not. The guy's name is actually William Gossett. And he went by the pen name of student because he didn't want his employer to know what he was doing, to know that he was publishing these stats papers. And he was actually the statistician for the Guinness Beer Company. And he needed to invent a way to statistically test whether or not the quality of beer in various vats was on average different from each other. And he figured out, and prior to him, people did, fanciful, maybe some z-test, maybe some comparative means. But he invented this thing called the t distribution because he realized, well, the normal distribution is fine, but we need to have a way to incorporate the levels of precision that are represented by more n's. So he invented the t-distribution. So today we are stuck with the name student, but it should be called the Gossett t-distribution. So I think it's fascinating that beer played a role in all this. And this is not that far away time-wise. It's only in the early 1900s, late 1800s, this happened. So only from the past 100 years or so, we've had this test at our disposal, and it's possibly the most commonly used and useful kinds of frequent statistics that you're going to use. Invented for Guinness beer. Okay, so this is our t-distribution again. This is the standard Z, the perfect Z, right? Again, probably the perfect normal curve. And this is what a t-distribution looks when there's only a handful of people in the sample. This is where it looks when it's like 30. And the more people we get, the closer we get to Z. So 30 tends to be around the number where we think that the t-distribution has its most, or starts having value. Below 30, it's not as valuable, but don't worry about that too much. Okay, so the distribution of t is similar to the Z, which is the standard normal. It's centered at 0, but instead of defining the spread by standard deviation, it's done by number. The more numbers we have, the more tighter and higher it gets. The Z does not do that. So we have a sample of 225 children whose mean IQ is 101 and whose standard deviation is 10.5. First thing we're going to do is calculate the standard error of the mean. And that is, again, standard deviation divided by the square root of n. That should be higher. That gives us 0.7. So our SEM is 0.7 here. Okay, that's a summary of what we have so far. And that's all you need now to compute a confidence interval for the mean. I can calculate my 95% confidence interval. I'm sorry about that. The color here, it's kind of fading out. So this is the formula for confidence interval. Can you see that? Hopefully, it's on your screen. It is your estimate of the mean plus or minus, and in brackets, the t-value times the SEM. Earlier, we used a Z value here. That's not typically kosher, but it worked for one particular reason, and that was for that particular case, Z and T were equivalent. Okay, but from now on, for confidence intervals, use that formula. All right, M is the mean of our sample. So for my 225 kids, the mean amongst them. If I'm doing ages, the mean age in this room, that's M. The SEM is, again, my standard deviation divided by root M and the t-value. So how do I get the t-value? We look it up. Life is easy, right? Where on page 412 of your textbook, or you go to this website or any number of t distribution calculators to get the right t number. What do you need to find the right t number? You need the degrees of freedom. What's the degrees of freedom again? Thank you. Sample size minus 1, exactly. So if you go to the back of the book, you'll find. You guys planned that? That was pretty good. Okay. Okay. So you're going to need the level of confidence you need as well. So we chose 95%. Again, when I ask you questions on exam or something, I'll probably stipulate 95%. If I don't assume it's 95%, but I probably will stipulate the number. Okay. So you're going to need the level of confidence, and you're going to need your degrees of freedom. Okay, so 95% is an alpha of 0.05. Your degrees of freedom here is 224, n minus 1. From page 212, you look it up, it's 1.96. You've heard that number before, 1.96. Well, that's amazing, right? Where's 1.96 come from? Does that sound familiar? Where is it from? Where'd you hear that before? That's your Z equal 2, exactly. That's why it was okay for me earlier to use the Z score, even though that's not typically kosher, because my N is so large here. My N is so large that my T distribution looks just like a Z distribution. So it's not surprising that I got the same number, 1.96, that I would have gotten from a Z distribution. And it gets even larger, it gets even closer to the Z score. Okay, so now we have these numbers. We plug it in. Right, I ask it's identical Z score. Why? Because, right? Plug it in and we get, what do we get? We get this. Can you see that? It's kind of bad color. 101, which is our mean, plus or minus these numbers here, 1.96 times my SEM. So 101 plus or minus 1.37, and that's my final answer. Okay. Somebody interpret that for me. What is that saying in lay language? If this is my attempt to compute the average IQ for 10-year-old students, what is that saying? Yes. Yeah, it's a tough one.
Basically that like between 99.6 and 102.4, you had an infinite number of samples that you're 95% confident in your mean.
That's right. Yeah, well phrased. You went deeper than I expected people to. In fact, we're saying that we're 95% confident that the true IQ of 10-year-olds is between these two numbers here. Yep. Good times. What if I'd asked the question, without doing all this work, ask you, is the mean IQ of 10-year-olds 102? That was the question. I asked you to do so not in a hypothesis testing way, but in a parameter estimation way. Well, you could have gone through all of this, collected the data, and found the same stuff, and say, look, 102, is it in that range? Yes, it is. So, yeah, the answer to that question would probably yes. With 95% confidence, yeah, the mean IQ of kids is probably 102. Okay, there it is. So 95% probability that the true population mean lies between these two numbers here. Okay. Could we have made a 99% confidence interval instead? Yes, we could have. What would be different? What would I have done differently to create a 99% confidence interval instead of a 95% confidence interval? Everything else would have been the same except for one number. Yes. The t-distribution number would be different. I'd go to page 412 and look up a different number. I would get t equals 2.58 in that case. And I plug in those numbers and I get this. Well, that's 95. Oh, I didn't do the math apparently, so you can do it instead. Okay. Right. So if you notice, this is exactly in between those two numbers. There's symmetry there. Why? Because we made it that way. I said it's plus or minus this amount. That's not usual. For most kinds of studies, when we compute confidence intervals, it tends not to be symmetrical. There tends to be a lot of skewness, right? But the way we just computed it, yes, there's symmetry. For the examples that you will do, there will always be symmetry because we use this methodology. So if we want to compute a confidence interval around something that's not a mean, like a proportion or an odds ratio or relative risk, for example, let's say I want to figure out the proportion of people in this room who are left-handed, right? Let's say I figure out that 15 of you are left-handed. So 15% of you are left-handed, let's say. And I want to use that information to project whether or not it is representative of the true rate of left-handedness in the university. That's not a mean. I'm not saying that there's a mean number of left-handed people here. I'm saying the proportion is this. I can't use the method I just showed you. The method I just showed you is just for means. And I'm only going to ask you to just do means. For proportions, we use something called a binomial distribution, not a t-distribution. And we're not be doing that in this class. Just beware, there are different distributions for different tasks. Okay, and that's actually, it's a pain in the ass. It's actually quite difficult to do. Usually let computers do it. Okay, because calculation is not straightforward, almost always done with our toys. And they're not symmetrical. Okay, but always the larger the sample size, the smaller the interval. That's why we like to have large samples. We get a tighter estimate of our parameter. The other weird thing about proportions is the closer it is to 0.5, it gets really wide. So let's say I figured out the 0.49 or 49% of you are left-handed. And I use that information to construct a confidence interval for what the true proportion of left-handedness is in this university. I'm going to get a huge confidence interval. Why? Because 0.49 is not that different from 50-50. And 50-50 is a really difficult thing to model. So for proportions, you know, the more extreme, the better. The easier it is, the more tighter the estimate. Okay. When we are graphically depicting confidence intervals, there's a variety of ways of doing it. The most common way, or the most useful way, is like this. So we have these bars here that show us the confidence intervals, and here are the point estimates. Right by looking at that, we can see, what's this? This is of the percentage of females in a sample. This is age group. Right? So even though our point estimates are quite different, we see that with our 95% confidence intervals, there's actually a fair amount of overlap. If I draw a line over here, I can say that, you know, most of my samples would accept a parameter estimate here as being in my range. So look at a real life example. This is an epidemiological study of a large group of people exposed to a variety of pollutants. And we looked at their characteristics to see how associative it was of their risk of dying. Okay, so here's the data. It's from an actual paper. So here we looked at the percentage of net change in number of residents between 1986. This is relative risk. Remember relative risk from last time? Or that is? Okay, what's the magic number for relative risk? The number that tells us nothing's going on. If relative risk equals blah, then the risk of the exposed group is not different from the risk of the unexposed group. What number is that? Sorry? 1, that's correct. All right, so we want to know, really, are these risks different from 1? Also, when relative risk is below 1, what do we say is going on? We said that if relative risk for smoking and lung cancer is like 4, then the risk of having lung cancer if you're smoking is 4 times greater than that of non-smoking. What if it's less than 1? What if it's 0.85 or something? What's happening there? Is it like riskier if you don't smoke? Yes, it's protective, we say. Okay, so let's look at this now. There's real data again. So this is the net change in the number of people living in this area. So 0.85. So that means the more people that live in this area, the less chance there was of dying. And here's a confidence interval. It could actually be anywhere between 0.81 and 0.89, 95% probability. Okay. Is 1 in that range? No, 1 is not in that range. Therefore, we're pretty certain this is real. If 1 was in this range, then we could say that within that 95% confidence interval, within that 95% probability of what's happening, it's possible, if not probable, that nothing's going on. So let's take out all the cases where 1 is in the range. That's gone, that's gone, that's gone, right? And that leaves 1, 2, 3 cases where we think something's happening. That's really how useful confidence intervals are. Just by looking at it, I can go right away, nothing's happening here, here, here. So this one, Gini coefficient, that's income. So the more income there is, the less likely you are of dying. That's nice to know. Okay, so that's, when you read papers now, you'll see data almost always presented like this with confidence intervals. That's how you read them. If they don't state, and they should state, it's probably 95%. Okay, your homework says, first of all, the answers in the comments section. When I convert everything from Google Slides or to Google Slides, the comments are all lost. So I'm going to have to recompute the answers for you. If you don't get them by like tonight or tomorrow morning, email me, remind me. But they used to be in the comment section. So just compute confidence intervals for both 95%, 99% for that scenario, and also those numbers there. It's a lot of stuff. You're okay though, right? I don't see any great distress in your faces. All right. How about you guys? All right. Okay. Bye.